Hello, everybody. My name is Heath Skarlupka. I work for the UW Carbone Cancer Center as a DevOps engineer. Today, I'm going to be talking about how we built our CI/CD Terraform pipelines using Azure Devops. So we're a small DevOps and security team with big plans to create a HIPAA compliant platform in the cloud. A couple of things that we're trying to build out now are a clinical data store using Smile CDR. So that's going to hold FHIR messages from UW Health that we can use for future research. We want to build out several three-tier web apps. One of them is called CBioPortal, and this allows you to view cancer genomics data from cancer studies. We also have data scientists that want to build ETL pipelines using Azure Data Factories with the ultimate goal of creating data marts. One of them will be an OMOP database that uses a common data model that's used frequently for healthcare research. So scientists from a different university, say, might give us a query to run against our OMOP database that will produce some data for them to do research with. We're also building out a process for doing de-identification of data using the software called DataVant. And we want to be able to have data scientists and PIs be able to do live data analytics from VMs in the cloud. So this is a lot of stuff. How are we going to build all of this with such a lean team? I knew that there were a couple of things that we needed to do from the beginning to get this right. The first one was automation. We needed CI, CD infrastructures code pipelines. There was just no way around it. We couldn't have Terraform that needed to be applied from somebody's laptop to several different subscriptions in dev, staging, and production. We wanted to reduce the burden of technical debt on DevOps engineers. That meant that we needed tests for our infrastructure's code. And it also meant that we needed a way to automate host image updates. We wanted to be able to add value elsewhere and not spend time patching machines or introducing bugs into our systems. We also wanted to reduce the burden on our security engineers by building strong compensating controls early. So one of those controls is that as a DevOps engineer, I don't have write access to staging and production accounts. All of the changes that I make must go through our infrastructure's code pipeline and be peer reviewed before they get pushed out. And this way, the modules that we wrote that had predefined security parameters don't get inadvertently changed through ClickOps or removed. So it's one less thing for the security team to worry about. So let's talk a little bit about our continuous integration strategy. So a typical workflow for us is an engineer will grab a ticket from our backlog. They'll check out a new branch in a Terraform repository, write some Terraform code, and then push those changes up to the remote repository. And in our case, we're using Azure DevOps for our ticketing system, for our pipelines, and for our Git repositories. There's no reason why you couldn't use GitHub for storing the code. And Azure DevOps works with AWS and Google clouds as well. So Their Azure DevOps service connections allow you to connect to multiple clouds and sort of abstract that. So that's really nice. So after your code is pushed up, an engineer would make a pull request and have their code peer reviewed. And that pull request creation would automatically start our CI pipeline. And until those tests pass, the process repeats itself. So you find a bug in your feature branch, you make a change, save it, and push it up, and that'll automatically trigger the CI job to start from the beginning again. So there are two CI jobs that we run. The first one's called TF-lint, and it's linting Terraform code. This is nice for when an engineer peer reviews your code. The grammatical errors, if you will, are removed and don't need to be reviewed. And then the second test that we run is TerraTest. And TerraTest is a piece of Go software that allows you to deploy your Terraform code in a development environment. It builds out the resources, and then you can run tests against that. So you can make sure that a VM got created or that a subnet was properly created in a VNet. The TerraTest has testing modules for all the different clouds. And then after your tests pass or don't pass, TerraTest will go through and delete all of those resources. So you don't have any messes being left behind in your development environment. So if you had to do all of that setup in Azure DevOps by hand, it would be a lot of clicking. And so there's actually a Terraform module for Azure DevOps itself. And so this is an example of setting up a build definition, which in Azure DevOps is a pipeline. And here we're telling it to use YAML, and we always store our pipelines in the pipeline directory in the repository. And then finally, we want to set up a branch policy build validation. And what this tells Azure DevOps to do is block any merges to the staging branch until we have a successful CI run. And you can replicate the same thing on other branches too, like your main branch. And so with that bit of Terraform code, here it automatically created this new pipeline for us for the CBio portal Terraform project. And if you drill into into your pull requests, you can see that one of the required checks is that this pipeline builds successfully. So let's look a little bit closer at the pipeline definitions. So if we look inside of our staging YAML file, here we're telling it to run the TF-lint and the TerraTest job. And if I drill down a little bit deeper into the TerraTest job, I can see that I am deleting the remote backend and creating a local one temporarily because I don't want these changes to be permanent. And then I'm telling TerraTest to run. And you can see we have a very simple test here. We're telling Terraform to do an init and apply, and then we're telling it to destroy those resources when they're done. So this is fairly basic. Once a more mature test might be to see if the cBio portal web servers running, maybe you would give it some fake data and then run a query against that and get some result. And so if we look at a pipeline run, here we can see Terra tests going through and creating all these resources for the cBio portal project. So after the continuous integration step and the DevOps engineers happy with the code they've written and they've gotten a peer review, they're going to want to move on to merging that code and getting it into staging. So, like I said, the tests pass, and what Terraform will, or what our pipeline will do is run a Terraform plan in the staging environment. And you'll notice that for now, it skips the apply step. And that's because we want to give engineers a preview of the changes that are going to happen in staging or production. So the plan, might show some resources being added, might show some resources being destroyed, and an engineer will have the opportunity to decide, is that really what I wanted to have happen? Let's say they're good with that, and then they merge their pull request, and this automatically kicks off our continuous delivery or deployment step. And as you can see in this step, not only is the plan run, but the apply is run too. Finally, what we do is we use the Azure Devops API to automatically create a staging to production pull request. This is a nice step, automated step, because now it creates an artifact somewhere that someone needs to review, and ensures that your staging environment or your production environment doesn't get too far behind from your staging one. If this was a process that someone had to do by hand, it might get forgotten, and then you might be several versions behind in production. So let's look at these pipelines a little bit closer. Again, if we first look at the staging pipeline, we can see that we're initializing a backend, and then we're doing our Terraform run. And if we drill down into the Terraform run YAML file, you can see we have two different tasks. We have a plan task, and then we have an apply task. On the apply task, we've added a conditional to make sure that it doesn't apply when we're doing a pull request. Right, again, we don't want these applies going out until the engineer is comfortable with the changes that they're going to make. So it's only on merge that the Terraform apply will run. And so the last part of the continuous deployment pipeline I wanted to show you was the job that we use for creating the staging to production pull request. And so you give it a fairly simple payload where you tell it the source and target branches. And in this case, we're adding the build ID to the title. And then we run a curl command that hits the repository's endpoint to create a pull request. And again, we've added a conditional here to only run this on merge and not during a pull request. So here we can see the Terraform plan in action, and these are the proposed changes that it's going to make. And again, if the engineer is comfortable with this, then they would merge their pull request. The last bit of automation that I wanted to talk about today is how we do automated host image updates in Azure. So we have a pipeline in Azure DevOps that is scheduled to run every night, and it goes through and builds images for all the different images that we have. And in each one, it does an apt-get upgrade. So we know that we have the latest version of packages in the kernel. We also use GOS tests for ensuring that certain packages get installed or services are running properly. This is kind of our first guard to make sure that, like, let's say an update to the kernel doesn't maybe inadvertently make Docker, not start or something like that. So after those tests pass, then the images get published to our staging shared image gallery in Azure. And then within about half an hour, our virtual machine scale sets automatically detect a new version of their image and will automatically start applying rolling image updates. So it will pick 20% of the servers in the scale set and replace them. We've set up health probes on each one of the scale sets to ensure that if something bad were to happen, the server doesn't come up, then Azure will automatically perform a rollback and the pipeline stops. As long as the health probes complete or are successful and all the VMs have updated, then what we'll do is copy those images to our production shared image gallery. And what's critical here is that we're not rebuilding the images, but we're just making a copy of what we created earlier. And this ensures that we're using the same artifact in staging and production, because you could end up with a race condition where maybe you get a newer version of Python, say, because you waited a few hours and a new package had landed in the repository. So by doing a copy of an existing image and not building a new one, we're ensuring we're using the same exact image. So once that's copied over, the same thing happens again in production, where the virtual machine scale set sees a new image version and automatically starts the rolling updates. And again, if the health probes fail, Azure would automatically roll back to the last healthy image. So in the top left corner, we can see how we can add a cron style pipeline trigger. This is a fairly simple one that tells it to execute the staging branch at midnight every night. I also added a bit of Python to automatically detect what the next newest version of the image should be, and also to create a end of life for these images, so that way they don't get inadvertently used and we exceed our SLA for patching. And at the bottom, we have our packer command that we run. Again, a fairly straightforward packer build command, which points at the packer file for each of the images that we build. And then this is an example of like a GOS test that we run. Again, it's a YAML file. And here we're checking to make sure that the Docker got installed. We're checking to make sure that the Docker service is running. And then we're also checking to make sure that some critical images that we need to be running have gotten pulled down. because in our compliant environment, we're very strict on outbound network rules. So we don't want to be doing Docker pulls in a live environment. And the other thing that this gives us is that we're able to package these Docker images right into our VM image and have created artifacts. So we're not inadvertently pulling down a newer version of a Docker container that we hadn't tested in a dev or staging environment. So through these three examples of automation that we've done, we can ensure that every infrastructure as code change is tested and planned for before being merged and applied in staging and our production environments. So this makes it really nice for an engineer to be able to make incremental changes to their code because they're not having to worry about time spent creating development environments. And so this makes most of the changes that we make maybe only several lines of code. As I said at the beginning, we've removed all write access for myself in the staging and production environments. And this has ensured that there's almost zero drift between our infrastructure as code and the infrastructure that we have built in our staging and production accounts. And I was surprised at this at first. I thought that this was going to be a real hassle not to have write access to these environments, but once you get used to using pipelines, it becomes a lot nicer to develop your code that way instead of having all of these extra permissions. We've written a lot of Terraform modules that ensure that compliance controls like encryption at rest and encryption over the wire and default firewall rules are automatically set up. And this makes it really nice to have several Terraform repos that can use these modules. Finally, value add tasks like supporting researchers replaces repetitive tasks like OS patching. If you guys have any questions, please look below. Thank you.